Alright, welcome back. This is going to be another video in the Wild Networking series where I focus on network engineering as is out in the wild as opposed to on a test or in a classroom. So out in the wild, just free, available for anyone to go and look at, are something called design guides. A lot of vendors put these out. They're basically, in some sense, advertisements because they'll explain a situation that they're actually selling a hardware device to solve. So what we're doing here is we're reading through the design guide offered by Cisco for campus LAN and wireless LAN designs, and we can see already we've read about the access layer, and sure enough they are recommending access layer platforms for us to purchase, but this is just setting it up in my lab and trying to design the best possible network, which this is certainly a good resource for trying to do that. I'm not going to be ordering the Cisco Catalyst 9400 just for my home lab, but what I will be doing is picking out a device that I want to use for my access layer just based on what I have available to me in GNS3. And I will be taking the advice given in this guide for how to pick the correct device and how to make sure that my network is designed properly. So the biggest thing they recommended was to have your uplink ratios proper. So your uplink ratio is the amount of bandwidth that you expect to come in through your access ports that connect out to the users of your network, as compared to the amount of bandwidth that is allowed between your access layer and your distribution layer. So you want that ratio to be greater than 1. You actually want more traffic to come into your access layer than your or you actually want your access layer to allow more traffic in than your uplinks can handle. And that might seem counterintuitive because you might think, oh well, if that's the case, then there's just not going to be enough bandwidth on my uplinks. But not every port is going to be going out to a device that continually maxes it out all the time. In fact, even in really heavily utilized devices, it's rare to meet that full link speed of the port. So that leaves you with some unused bandwidth in your uplinks that you can plan for, and you can have a valid network design where there is that overhead. Where it gets to be tricky though is just knowing what that overhead is and calculating that properly, because you can run out of bandwidth there, which is a problem. And then similarly, you can set up too many links there, which can be a problem too, because then you just gotta do more to your network than is necessary. So we learned about that. We learned that the recommended ratio is 20:1 max between the access and distribution layer. So let's pick out a a distribution layer that's going to work, and access layer device. So between videos, I installed some more devices. I've got Cumulus. I had that before, but I've also got Extreme. I've actually got a Cisco, and I've got a ONOS. So what we want on our access layer is probably 1 gig links or lower, and then in our distribution layer we're going to need 10 gig links. So let's test what we've got so far. Let's take a look at what kind of links we have available in our distribution layer right now. So you can see our distribution layer here consists of 2 Aruba OS CX devices. Alright, and I'll pause it. I'll be back shortly. Alright, I am back, so let's see what kind of links I have available on my distribution layer right now. Alright, so it looks like I've got 1 gig links only on my distribution layer. I don't think that's going to be enough for me. Let's see what I've got on my core layer. I'm pretty sure I've only got gig links on my core layer, which again isn't going to be enough. But I'll open up a few of these so we can check them all at once. Here I got to the boot layer. Bootloader. This is a nice feature that they've automatically enabled spanning tree. Nice, nice, nice. I like it. I'm not going to disable it. Enhanced security mode. I don't want that. Security is just not a big thing for me. Disable telnet. No, see, security is just not a problem for me because I'm just using this in the lab. But I really like that they they ask you those questions, because if you were to deploy it out in the real world, you would want to be concerned about security. Okay, so here's all the ports we've got available on here. Oh, this is not, let's see here, link state. So we want to see what the ports are capable of. Link scan, maybe that's it? No. Information, that sounds right. Ah, perfect, yeah, so, well, I don't see it. I'm trying to figure out what kind of port speeds, line rates I can do on this. Now, some of these, as we read, are a little bit different than others, where you can have a fixed switch where all the ports are on there, and when your only option is to throw the whole thing in the garbage with all the ports on there. The other option is a modular switch where you can take the module with the ports out and then throw the rest in the garbage. So it's basically like, how many different ways can you throw something, one of these switches, in the garbage? Modular switches, you can throw different pieces in the garbage. Fixed switches, you only have the option of throwing the whole dang thing in the garbage at once. Now I wish I could see. What does an R mean? R means ready, E means enabled, but I can't tell which speed I can do on it. Okay, well, it's now configured as ether type primary. I'm not sure what that means. I wish I could see leak scan. Yeah, I don't know. I don't know if I can use this one because I'm having trouble. I guess I could Google it quick. Service port. Oh, I found it. Okay, I found not the password, but whoa. Okay, well, here's our big ones. Yeah, so this is definitely gonna belong on the access or even the core layer. You know what? I think I'm even gonna get rid of those junipers at the core layer because those junipers are just gig. So I could probably even do this extreme here on the core, the Arubas on the access, and then the junipers on the distribution. That would probably be better because these extremes, you know, we're talking. I can do 100. I can go as high as 100 gig. I mean, that's just absolute. That's extreme. So, but on these junipers here, let's see what we got. So we've got gig ports. So I'm assuming a gig port is only capable of a gig. It's probably capable of going lower than that, but I doubt it's capable of going higher than that. Let's see if we can find a command for that. Yeah, so we're capable of going low. Oh, we actually are capable of going a bit higher. We're capable of going up to 10 gig. But on the extremes, we're capable of going much higher. We're capable of going up to 100. But on the Arubas, we're not capable of anything but 1 gig. So I almost want to just use the extremes for everything because, or I guess we can't go down to. Oh yeah, because we can go. It just has the most options. But I definitely want this to be multi-vendor. I want to get practice with that. So we're definitely going to go with the extremes at the core. So let's delete our core layer here, and then we'll rethink it once we learn more about the core. This one we're going to learn about the distribution layer yet. We already learned about the access layer, so we do know kind of more what we want there. We want, I think, a lot of port density. Oh, why is this not working? Okay, well, we're not going with the Cisco because for some reason it's just not working today. I'm pretty sure it has worked before, but it's not working now. The Cumulus would be a good one to go with as well. There we go. So let's see what we got for the Cumulus. Oh. Oh, so it looks like these Cumulus Linux boxes have really, really good options on here as well. It has as much versatility as does the Extreme, but we've only got 6 ports to play with on these. So you know what? I might put the Extreme on the distribution layer because there's more ports to play with on it. Yeah, we've got 12 on the Extreme, but we've only got 6 on the Cumulus. Okay, so the Cumulus is going to be the core. There we go. The Extreme is going to be the distribution. And then I'm thinking I want the Aruba to be the edge. I guess I'm not sure about that still. I did kind of want a Juniper in here just because Juniper is the one I've spent the most time on in terms of certification. But let's go with an Aruba at the edge. Yeah, I don't think it would make sense to put the Juniper at the edge. Only in the, yeah, so we're going with the Aruba at the edge. Okay. There we go. So, yep, and then we learned in the last video how to connect that up to the distribution layer. At least I thought we did. This looks kind of confusing. I guess maybe that's what we'll learn now in the distribution layer video. Yeah, so we can get kind of a sense of the design. For now, let's just configure it up the way this diagram looks, where we've got 2 port channels up to each distribution. We'll do the last and second to last ports. And then here we'll start the first. Okay, so very quickly running out of ports on here. That could be a problem. If it is, we can use the... Oh, we can't use the Cumulus because that has even fewer ports. Alright, so that looks a lot better. Yeah, I mean, let's do some reading about these before making any more decisions. So this is going to be the distribution layer. The distribution layer supports many important services in a network where connectivity needs to traverse the LAN end-to-end, whether between different access layer switches or from an access layer device to the WAN. The distribution layer facilitates this connectivity. Scalability. At any site with more than 2 or 3 access layer devices, it is impracticable to connect all access switches. Okay, well this site here we're having okay. The distribution layer serves as an aggregation point for multiple access layer switches. The distribution layer can lower operating costs by making the network more efficient, requiring less memory, by creating fault domains that compartmentalize failures or network changes, and by processing resources for devices elsewhere in the network. The distribution layer also increases network availability by containing failures to smaller domains. Reduce complexity and increase resiliency. The campus wired LAN has the option to use a simplified distribution layer in which a distribution layer node consists of a single logical entity that can be implemented using a pair of physically separate switches operating as one device, stackwise virtual. Or using a physical stack of switches operating as one device. Resiliency is provided by physically redundant components like power supplies, supervisors, and modules, as well as stateful switchover to redundant logical control planes. This approach reduces complexity of configuring and operating the distribution layer because fewer protocols are required. Little or no tuning is needed to provide near-second or sub-second convergence around failures or disruptions. Two-tier design. The distribution layer provides connectivity to network-based services, to the WAN, and to the network edge. Network-based services can include, but are not limited to, Wide Area Application Services, WAAS, and WAN controllers. Depending on the size of the LAN, these services and the interconnection to the WAN and Internet edge may reside on a distribution layer switch that also aggregates the LAN access layer connectivity. This is also referred to as a collapsed core design because the distribution serves as the layer 3 aggregation layer for all devices. So in a 2-tier design, the distribution layer also serves as the core. We're not going to have that design though, we're going to use a 3-tier design. So you've got, and it looks like your distribution layer. Now this is interesting because I see 3 tiers here. I don't see 2 tiers. I see tier 1 up here, tier 2, and tier 3 down there. So I don't know what they mean when they say 2-tier. Is one of the tiers not considered a tier? Is it not considered? I guess the server room here doesn't belong to the LAN. So this is considered a not a tier, but another LAN, because there's so I guess this is a really confusing image for me. I wish they would actually mark tier 1, tier 2 on here and not just kind of leave that up to the reader of this to determine that for themselves. But I think this is going to be tier 1 up here, and then this is going to be tier 2 down here. This is the access layer, this is the collapsed core and distribution layer, and then this is just a switch that comes off of it, kind of like how these WAN wires would come out of it, your firewall would come out of it, your wireless. So basically, the way I would like to see this redrawn is to just expand out this rectangle here and then put everything in here in the same rectangle as this. That would make it a lot more clear. Alright, but there's also the 3-tier design. This is the kind of design I'm going to be using in my lab. Larger LAN designs require a dedicated distribution layer for network-based services versus sharing connectivity with access layer devices. As the density of WAN routers, WAAS controllers, Internet edge devices, and WLAN controllers grows, the ability to connect to a single distribution layer switch becomes hard to manage. When connecting at least 3 distributions together, using a core layer for distribution connectivity should be a consideration. There are several factors that drive LAN design with multiple distribution layer modules. The number of ports and port bandwidth that the distribution layer can provide affects network performance and throughput. So I made sure to have a lot of throughput on mine and a high number of ports on the distribution layer. I could have made a different choice and put this up at the core layer, but I think it's more advantageous to have a higher number of ports at the distribution layer than it is at the core layer. Network resilience is a factor when all LAN and network-based services rely on a single platform, regardless of that platform's design. It can present a single point of failure or an unacceptably large failure domain. Change control and frequency affects resilience. When all LAN and WAN and other network services are consolidated on a single distribution layer, operational or configuration errors can affect all network operation. Geographic dispersion of all LAN access switches across many buildings in a larger campus facility would require more fiber optic interconnects back to a single collapsed core. Like the access layer, the distribution layer also provides quality of service QoS for application flows to guarantee critical applications and multimedia applications perform as designed. So here's the 3-tier design. Of course, they don't have any. So in the 2-tier design, they have 3 rectangles, but only 2 of the rectangles represent a tier. One of the rectangles, I believe, belongs to this rectangle, but in the 3-tier design, they don't have any rectangles at all. It's like, show me where the tiers are, for God's sakes. But I think the tiers are going to be here. Like, this cloud is a tier, and then this is a tier, and then this is a tier. Right here, there's actually no tier over here. These are all part of the. So let me actually do that. So just to make this really clear, I'm gonna open up MS Paint. Actually, you know what? I don't even have to open Paint. So we'll just circle all the tiers of this network design. So here's tier 1, which is the core tier. Now, to circle tier 2, the access layer tier, we're going to have to draw a much bigger circle like this. There we go. So this is all tier 2. And then tier 3, that is pretty self-explanatory. We've already read the design guide, everything it had to say about tier 3, the access layer. So we know this is tier 3 here. That's the simplest one. Tier 2, the distribution layer, looks like the most complex layer because you have a lot of different kinds of things plugging in at tier 2. Tier 3, these end devices are not nearly as complicated as things like a LAN controller, a firewall, or a WAN device. It also looks like tier 1, the core, is pretty simple as well. They didn't even think to actually put devices in there, but we'll get to that later. Looks like we're going. So I'm not sure if tier 1 would be typically referred to as the core or the access, but I'm gonna call the core tier 1, distribution tier 2, and the access tier 3, unless I see it called out differently as I read on. All right, but that's it for their explanation about the distribution layer. Let's take a look at what kinds of switches they recommend for that, and let's see if it's different than what they recommend for the edge. So one thing that's really nice about Chrome now, there's tab groups, so we can add a tab to a new group. We're going to call this distribution. Okay, and now we can drag these other tabs into that group. There we go. So we've got 3 tabs in that group. Now let's go back and look at, well, first of all, let me save this. There we go. And then we'll go back and look at the devices they recommended for the edge or the access layer. Okay, so let's take a look at some of these distribution devices, see if they've all got something in common here. So we've got, the first one is the Cisco Catalyst 9600 switch series, and this is modular. That's important to note. That's always a good thing to consider, whether you want modular or fixed switches. Because you can end up saving money if you don't need a higher line capacity. You can get a module that has smaller capacity. And then if you do need to upgrade, it's a lot easier to upgrade a modular switch. You just buy a new module and unplug the old one, plug in the new one. And sometimes you can even just do it on the fly, because if you have another slot open, you can just wire everything up with the new module, put it in, and then split second like that, you just switch over to the new module. So there's really fast switch over things you can do as well with modular switching that you can't do with a fixed switch. But yeah, here's a Catalyst 9600. You can see it's a big switch, but that makes sense because this is for the distribution layer, which has a lot of complex big things plugging into it. So yeah, we got QoS. That's another thing you want on your distribution layer. IP routing. Yeah, okay, let's see how this compares to the other one. See, the thing that gets me though, and I talked about before, is there's no pricing on this. Like, I wish they were more transparent about their pricing. I mean, maybe we can get one off of Amazon or something. Now there's different kinds. Yeah, so here's the different kinds you can order, and the thing is, you've got to order, because it's modular, you have to order the form factor and the modules. You have to order multiple things. So I wish they were more clear about this. But let's go to Amazon quick and just see, buying something like this off Amazon, what would it cost if it's available? So it looks like you can't buy this sort of thing from Amazon. Huh. Alright, let's look at the next one and the next one. Okay, so these look like they're fixed switches, they're not modular. Okay, and then these, I'm not sure about these. But basically what I wanted to see is, what's the difference between these and the ones that are recommended for the access? Are there any big differences that stand out? So here's a 9300, and that's different from a 9500 and a 9400. Yeah, so I guess the biggest difference I can see right off the bat, just as I'm looking at pictures of these, is we've got RJ45. So first of all, we've got high port density. Port density on these is much higher for the access layer. You know what? I think I'm going to close the 9400 because this just looks like kind of a more versatile router that's meant to be used for either the access or the distribution, and I want to see more clear differences between how routers are designed depending on where they're intended to be used. So obviously a router that's designed to be used in either case is not the kind I want to look at. But these are fixed switches, and then these are modular switches here. So that's a big difference between 9600s and 9500s. Now, what's interesting is it looks like 9300s and 9200s, those are both fixed. So it looks like they're not quite recommending a modular for the access. They're only really recommending it for the distribution layer. And the other thing, as I mentioned, is we can see port density is really high, and we've got we do have some slots here for fiber connections, but mostly we've got RJ45 connections. But that's quite a bit different here. You can see these devices here are all for fiber connections. Now we do have this device here, and I'm not sure what kind of ports these are. They look kind of unclear. I think they're RJ45, but yeah, I mean the port density looks about the same. But you remember, you do need a high port density on the access distribution layer as well. That is something we learned about. Where port density isn't as big of a concern is on the core layer, but definitely the access layer and the distribution layer definitely going to want to have a high port density, especially on the access layer. So here we've got 6, so we've got 12 times 4, and here we've got 1, 2, 3, 4, 5, 6, 7, 8 times 2, so 16, 32. So we've got 40 ports on here, and here we've got 24 times 2, so we've got 44 ports. We do have extra ports on the access layer than on the distribution layer. So yep, that's a big characteristic of your access layer. You want to have the highest port density, so the highest number of ports to plug into, but the line rate of each of those ports doesn't necessarily have to individually be super high. On your distribution layer, you still want a lot of port density, but you don't need quite as much as on your access layer. But you do want the capability for higher line rates on your distribution than on your access layer. That's going to be really important. All right, so next up is learning about the core layer. In a large LAN environment, there often arises a need, and I got to break here. I'll be back shortly. All right, I'm back. I needed to change my shirt quick. Core layer. In a large LAN environment, there often arises a need to have multiple distribution layer switches. One reason for this is that when access layer switches are located in multiple geographically dispersed buildings, you can save potential costly fiber optic runs between buildings by locating a distribution layer switch in each of those buildings. As networks grow beyond 3 distribution layers in a single location, organizations should use a core layer to optimize the design. Another reason to use multiple distribution layer switches is when the number of access layer switches connecting to a single distribution layer exceeds the performance goals of the network designer. In a modular and scalable design, you can co-locate distribution layers for data center, WAN connectivity, or internet edge services. In environments where multiple distribution layer switches exist in close proximity and where fiber optics provide the ability for high bandwidth interconnectivity, a core layer reduces the network complexity to n times 2 redundant links for n distributions down from n times n minus 1 divided by 2 redundant links as shown in the 2 figures. I like to call it n squared minus n divided by 2. I don't know, I just think that's easier. Alright, so okay, so yeah, so this is what you get from a core layer. So if you don't have a core layer, Now, why do you need a full mesh? That's what I'm confused about. I guess, well, you need a full mesh for IBGP, but you can use configurations or route reflectors. I guess you could get in a situation where you're oversaturating a link. Alright, the core layer of the LAN is a critical part of the scalable network, and by design, one of the simplest. The distribution layer provides the fault and control domains, and the core layer represents the 24/7, 365 nonstop connectivity between them, which organizations must have in the modern business environment where connectivity to resources to conduct business is critical. Connectivity to and from the core layer is layer 3 only, which drives increased resiliency and stability. Oversubscription ratios. For 3-tiered designs, increasing the uplink speeds between the access and distribution layer switches may require increasing uplink speeds between the distribution and core layers in order to maintain the desired oversubscription ratio. Determining the oversubscription ratio of the uplink between the distribution and core layer switches is fairly straightforward. You need to take into consideration the number of ports connecting the distribution layer switches to the access layer switches or switch stacks, as well as the speeds at which the ports are operating. Oversubscription between the distribution and core layer switches. So just like with the access layer, you can have the uplinks oversubscribed because they're not going to be maxed out all the time, but you got to make sure your ratio is such that you do actually have enough bandwidth most of the time when you do have enough bandwidth for your uplinks. So here's the design here. For example, let's say your distribution layer switch is a stackwise virtual pair that supports a building with 4 floors. Each floor has 2 IDFs, wiring closets, and each IDF has an access layer switch consisting of 4 48-port switches along with a 2x25 Gbps uplink module in 2 of the switches within the stack. The total number of 25 Gbps ports required at the distribution layer is 4 uplinks times 2 IDFs per floor times 4 floors, 32 ports. This configuration would provide up to 32 times 25 Gbps equals 800 Gbps bandwidth between the distribution layer and access layer switches. Simply keeping existing 2 times 40 Gbps uplinks would only provide up to 80 Gbps between the distribution and core layer switches. This would provide an oversubscription ratio of 800 to 80 or 10 to 1 between the distribution and core layers. Depending on your business requirements, this may be insufficient. Now, they recommended 4 to 1 before, so yeah, that might be sufficient, might not be sufficient. You just gotta know what your business requirements are, and you need to have bandwidth monitoring on your links too to see what the actual saturation is. If it's constantly oversaturated, yeah, a 10 to 1 ratio is just not right for your business requirements. Okay, increasing uplink speeds. You could choose to add additional 10 Gbps links between the distribution and core layer switches, possibly operating in a layer 3 ether channel configuration. However, this would require additional 40 Gbps switch ports at every distribution layer and core layer switch. More importantly, it would require additional fiber optic pairs between the distribution layer switches and the core layer switches. In a large campus deployment, the core layer switches may be located in a centralized data center in a different building. If insufficient optical pairs exist, then additional optical cabling would need to be pulled between the centralized data center and each of the buildings. This could be a very expensive proposition, as existing conduit space between the buildings may not be capable of supporting additional cabling, and you run the risk of damaging the existing cabling in the conduit, resulting in an outage. Installing new conduit may involve getting the necessary right-of-way to trench and install underground conduit, on top of the cost to install the new fiber optic cable. An alternative way may be to upgrade the uplink speeds between the distribution layer and core layer switches up to 100 Gbps. Okay, so we'll have the ability to do that with the choices I've made in my home lab here. Cumulus at the top, then Extreme, and then Aruba at the bottom. So this will give you a 4-to-1 oversubscription ratio at the uplink between the distribution and core layers. So right here, that's much better. That's what they recommend. This would provide an oversubscription ratio of 800 to 200, or 4-to-1 between the distribution and core layers. As with the access layer, when deciding to upgrade the uplink speeds between the distribution layer switches and the core layer switches, you should keep in mind the following. The optical transceiver modules, which connect the distribution layer switches to the core layer switch platforms, have to interoperate with each other and have to be compatible with the fiber optic cabling between buildings. Due to the increased distances between buildings, single mode fiber SMF may already be installed between the distribution and core layer switches. This may help facilitate the migration from 40 Gbps to 100 Gbps between the distribution and core layers. Core layer platforms, the preferred Cisco switches used as campus platforms for the core layer are Cisco Catalyst 9600, which I think we saw before. Yeah, I've already clicked on those, so I think we looked at that before. And then Cisco Catalyst 9500. So it looks like they recommend the same switches for the access layer to be used in the core layer. And it sounds like in a lot of cases, it's pretty rare to actually need a core layer switch. Really just if you have an absolute gigantic network, or if you have a situation where you need a lot of distribution switches. You might be better off just using one of those switches for a core switch, so you don't have as many connections between each of the distribution switches. You can just tie them all back to a single to a core switch. And then sometimes it depends. Can I run a cable? Can I not run a cable? So. Yeah. Alright, but that's the end. So the capacity, density, and features are the primary differences driving platform selection. Both lead platforms have sibling platforms that may be appropriate for the core role in existing networks, or networks where the full capabilities of the lead platforms are not required. Okay, so next part is going to be design options, campus, wired LAN. And I think I'm going to stop here. It's been over an hour. I just need to take a break. So I'm trying to get okay, I'm going to have a higher highlight here. There we go. That'll take me back to my place a lot better. Yeah, I kind of tempted to try to push it and go on a bit further, but I've been going pretty far. Okay, I think this is going to be fine. Yep. Okay, yeah, that should be fine. So, yep, that's going to be it for this video. Thanks for watching. See you in the next one.